Hi students, good morning. Welcome back to our physics classes. So during the last chapter we have seen what is a thermodynamical system and how you can define a thermodynamical system and what are the state variables, how you can change the state of a system and what do you mean by a thermodynamical process, and finally we have seen the first law of thermodynamics and different types of thermodynamical process. From there, we are having two thermodynamical processes, that are isothermal process and adiabatic process. So, in this chapter, we are describing what is an isothermal process and what is an adiabatic process, and we are trying to find out what is the work done in an isothermal process and an adiabatic process. So, we can start with the first system. So, first process, that is isothermal process. Isothermal. As the name indicates, isothermal means during the process the temperature of the system remains constant. During the process, the temperature of the system remains constant. So, if the system increases its temperature, to maintain the temperature constant within the system, it will release energy to its surroundings. And when the heat temperature of the system drops, then it absorbs heat energy from the surroundings to increase its temperature, which means there is a heat transfer between system and surroundings so as to maintain the temperature constant. But we can't say that there is a perfectly conducting walls which separates the system from the surroundings. So perfectly isothermal process is a ideal process. It cannot be possible. But we can say that when this process is carrying out very slowly, then heat will get enough time to flow from system to the surroundings or from the surroundings to the system. So it is possible through only slow process, isothermal process, slow process, and it obeys Boyle's law. It obeys Boyle's law means at constant temperature P is directly proportional to 1 by V. That means P is inversely proportional to V. So PV equal to a constant. This is the characteristic equation for an isothermal process. PV equal to a constant. That is PV equal to K. PV equal to K is the characteristics equation for an isothermal process. So any isothermal process can be identified with this equation PV equal to K. If pressure and volume, the product of pressure and volume remains constant at any instant of the process, then we can say that it is an isothermal process. So we have already seen in the last chapter, any thermodynamical process can be expressed in terms of a graph which is plotted against pressure and volume. So the PV diagram for an isothermal process, PV diagram for an isothermal process is like this only. So V1 to V2, system expands from V1 to V2, so its pressure changes from P1 to P2. Its pressure changes from P1 to P2. So this is the isothermal curve. We can call that as an isothermal curve, which shows the PV diagram for an isothermal process. So we can find out the slope of this curve. What is the slope of this curve? Slope of this curve is changing y coordinate divided by changing x coordinate, dp by dv. You have to find out what is dp by dv for an isothermal process. For that you can make use this equation, that is PV equal to a constant. If you are differentiating this equation, we will get P dV plus V dV equal to 0. If you are using our properties of differentiation, this is product rule, P into dV plus V into dP equal to differential of a constant is 0, that you know. So P dV is equal to minus V dP. So dP by dV is equal to minus P by V. dP by dV is equal to minus P by V. This is the slope of an isothermal process. Important. This is an slope of an isothermal curve or an isothermal process. Is it okay? So this is an isothermal process in which the temperature remains constant for the system throughout the process, and there is heat transfer between the system and its surroundings. Then it is characterized by the equation PV equal to a constant, and that is PV is equal to K. Then isothermal curve for the isothermal curve is, that means the problem in PV diagram for isothermal process is like this only. So the process, slope of the curve is dP by dV, and it is found to be minus P by V. So that is the isothermal process. Now we can move on to adiabatic process. So in an adiabatic process, adiabatic process is characterized by change in temperature. Adiabatic process is characterized by change in temperature. So adiabatic process is identified by a change in temperature. So what do you mean by an adiabatic process, or what is the characteristics of an adiabatic process? Which means there is no heat transfer between the system and the surroundings. There is no heat transfer between the system and the surroundings. If anyhow the temperature of the system increases, no heat flow into the surroundings. Or when the temperature of the system drops, so no absorption of heat from the surroundings. Which means whatever may be the temperature change that will be observed within the system. That means isothermal process is identified by with a constant temperature, and adiabatic process is identified by a change in temperature. Okay, isothermal process is identified by a constant temperature throughout the process, and if during a thermodynamical process the temperature of the system varies, you can say that it is an adiabatic process. And moreover, there is no heat transfer between the system and the surroundings, and it's a sudden process. We have seen isothermal processes are slow process. Comparatively, adiabatic processes are sudden process. And the equation, it obeys Poisson's law. Adiabatic equation obeys Poisson's law. It says that PV power gamma equal to a constant. PV power gamma equal to a constant, where gamma is equal to Cp by Cv. Gamma is equal to Cp by Cv. Cp is the specific heat capacity at constant pressure, and Cv is the specific heat capacity at constant volume for the system. Heat capacity, specific heat capacity at constant pressure, and specific heat capacity at constant volume. That are Cp and Cv. So gamma is equal to Cp by Cv. So PV power gamma equal to constant is the equation for, characteristic equation for an adiabatic process. Again, we can plot the PV diagram for adiabatic process. So adiabatic process is like this. Again, it expands from system expands from V1 to V2, so the pressure changes from P1 to P2. The slope of the curve will be dP by dV. Same process, dP by dV. Slope of the curve will be dP by dV, and you have to find out what is dP by dV from this adiabatic curve. For that, you can use the characteristic equation for an adiabatic process. What is that? PV power gamma equal to a constant. So V power gamma into dP plus P into gamma V power gamma minus 1 equal to 0. Okay, then dP by dV we need. So V power gamma into dP equal to minus P into dV equal to 0. Okay, this is the differential for V power gamma into differential of P plus P into differential of V power gamma, that is gamma into V power gamma minus 1 multiplied by dV equal to 0. So V power gamma dP is equal to minus P minus gamma P into V power gamma minus 1 into dP. Okay, so dP by dV equal to minus gamma P into V power gamma minus 1 divided by V power gamma. V power gamma and V power gamma can cancel, it will become V power minus 1. V power minus 1 will become 1 by V. So that will become gamma into P into 1 by V. Simply that is gamma P by V with a negative sign. So here dP by dV, at last we are getting dP by dV is equal to minus gamma into V by V. This is the slope for an adiabatic curve. This is the slope for an adiabatic curve. Clear? So for an isothermal curve, we have already got the equation for slope dP by dV for isothermal is equal to minus P by V, and dP by dV for adiabatic you are getting minus gamma P by V, which is greater. Gamma is Cp by Cv always greater than 1. So we can say that adiabatic slope is more than isothermal slope. Adiabatic slope is more than isothermal curve by a factor gamma, where gamma is Cp by Cv. So from the graph itself you can find out whether it is a either it is a isothermal curve or an adiabatic curve. Suppose you will have two curves in a same coordinates. So we can have A, B and AC. From this it is clear that slope of AB is more than slope of AC. Slope of AB is more than slope of AC, that is steeper. So we can see that, we can say that AB is an adiabatic curve and AC is an isothermal curve, because slope of adiabatic curve is more than isothermal curve. That is why it is more steeper. So from the graph itself, we can predict whether the process is an isothermal process or an adiabatic process. So remember, when you are comparing isothermal process and adiabatic process, in isothermal process there is no temperature difference. In adiabatic process there is a temperature difference. Okay, and in an isothermal process there is heat transfer between system and surroundings. In an adiabatic process, no heat transfer between system and surroundings. Okay, characteristic equation is PV is equal to constant for isothermal, PV power gamma equal to constant for adiabatic, where gamma is Cp by Cv. Isothermal process, slow process, adiabatic process, surround process. Slope of isothermal curve is minus P by V, and slope of adiabatic curve is minus gamma P by V. Okay, so when an isothermal process happens, since it is a slow process and the temperature remains constant, its internal energy will not change. Because for an ideal gas, internal energy depends upon its temperature. So since the temperature remains constant, its internal energy also remains constant. But in a adiabatic process, since the temperature changes, its internal energy also changes. Remember these things. Now we can go for work done in isothermal process and adiabatic process. So we have characterized isothermal and adiabatics. Now we can go for work done in an isothermal process or an adiabatic process. Okay, so we can start with work done in isothermal process. So any thermodynamical process, the work done from expanding from V1 to V2 is given by integral V1 to V2 dW, that is integral V1 to V2 P dV. General equation for work done. So here you have isothermal process initially. For an isothermal process, we have PV equal to constant. Since it is an ideal gas, you can have this K is equal to nRT. since T remains constant. So N is the number of moles. So PV is equal to nRT. So this P you can replace by nRT divided by V. So this implies P is equal to nRT divided by V. Okay. Now from this integral, this P you can replace by nRT divided by V. So W will become W is equal to integral V1 to V2 nRT divided by V dV. N is constant, what is R? Universal gas constant, what is T? Temperature for an isothermal is also a constant. All the constants you can take out nRT into integral V1 to V2 1 by V dV. What is integral 1 by V dV? That is log V. So W is equal to nRT into log V within the limit V1 to V2 is equal to nRT into log V2 minus log V1. Okay, log A minus log B is log of A by B. So W equal to nRT log, this is natural logarithm, log V2 by V1. nRT log V2 by V1. And this natural logarithm you can convert into common logarithm with multiplying 2.303 RT log V2 by V1. Okay. ln 1 and n is equal to 2.303 log of 10. So that is the relation log is equal to 2.303 log. So this is natural logarithm and this is common logarithm. This is also written as log E and this is log 10. Okay, remember that. So W is equal to nRT log V2 by V1, that is 2.303 log V2 by V1, log V2 by V1. This is the work done in an isothermal process. So we are having PV equal to a constant. PV is equal to P, constant means P1 V1 is equal to P2 V2. So V2 by V1 will be P1 by V2. That will be, which implies V2 by V1 is equal to P1 by P2. P1 by P2. So this can be replaced by 2.303 RT log P1 by P2. This is in terms of pressure and this is in terms of volume. Okay, so very simple. We are having the general equation V1 to V2 dW is the total work done, that is PdV. Then using the isothermal equation PV equal to K, that is PV is equal to nRT, P replaced by nRT divided by V, just integrate. That's all. So finally we are getting as W is equal to 2.303 RT log P1 by P2 or V2 by V1. Okay, that is work done in an isothermal process. Now we can go for work done in an adiabatic process. So again, we are having the same equation. We are proceeding with the same equation. P V power gamma, W is equal to integral V1 to V2 dW. That is integral V1 to V2 PD. But here, for an adiabatic process, the equation is P V power gamma equal to constant. P V power gamma equal to constant. And you can take it as K divided by V power gamma equal to K divided by V power gamma equal to P. Now we can replace this equation W equal to integral V1 to V2, what is P, K divided by V power gamma dV. Since K is constant, K into integral V1 to V2, V power minus gamma dV. This is in the form h to the power n dx, that is K into V to the power minus gamma plus 1 divided by minus gamma plus 1. Okay, so W equal to K divided by 1 minus gamma into V to the power minus gamma, 1 minus gamma, 1 minus gamma within the limit V1 to V2. Here also within the limit V1 to V2. Okay, so W is equal to K divided by 1 minus gamma into V power 1 minus gamma divided by 1 minus gamma from the limit V1 to V2. This can be replaced by K divided by 1 minus gamma into V2 power 1 minus gamma minus V1 power 1 minus gamma. Since gamma greater than 1, you can interchange the order. So W equal to K divided by gamma minus 1 into V1 power 1 minus gamma minus V2 power 1 minus gamma. No problem with that. Means you just multiply by a negative sign both sides. Both sides means inside and outside. And according to our adiabatic equation, PV power gamma equal to a constant. So we can have P1 V1 power gamma equal to P2 V2 power gamma equal to constant K. So when you are taking this K inside, this will become 1 by gamma minus 1 into K into V1 power 1 minus gamma minus K into V2 power 1 minus gamma. Okay. Now you can make use that equation PV power gamma equal to a constant. PV power gamma equal to constant. So K equal to P1 V1 power gamma equal to P2 V2 power gamma. Is there any doubt for that? No. So W is equal to 1 by gamma minus 1 into this K you can replace by P1 V1 power gamma. So P1 V1 power gamma into V1 in 1 minus gamma minus P2 V2 power gamma into V2 gamma 1 minus gamma. V2 power 1 minus gamma is already there. V1 power 1 minus gamma is already there. That P you can replace by K you can replace by P1 V1 power gamma here and P2 V2 power gamma here. So this equation will become 1 by gamma minus 1 into P1 into this gamma V1 gamma into V1 gamma 1 minus gamma. So V1 power gamma plus 1 minus gamma. So that will become simply P1 power 1. So this is P1 V1 minus P2. That is the simple equation for work done in an adiabatic process. That is W equal to 1 by gamma minus 1 into P1 V1 minus P2 V2. Okay, but if you want, you can replace it by PV is equal to RT. So P1 V1 is equal to RT1, P2 V2 is equal to RT2. So this will become R divided by gamma minus 1 into P1 minus P2. R divided by gamma minus 1 into T1 minus T2. Remember, here we have considered only one mole of ideal gas. If there are n mole of ideal gas, so P1 V1 equal to nRT1. So in general case, you can take it as nR divided by gamma minus 1 into T1 minus T2 or 1 by gamma minus 1 into P1 V1 minus P2 V2. So this is the work done in an adiabatic process. So we have seen what is the work done in isothermal process and what is the work done in adiabatic process. So we have seen what is isothermal process, slope of isothermal process, adiabatic process, slope of adiabatic process, work done in isothermal, work done in adiabatic, and we compared isothermal process with adiabatic process. What are the properties of isothermal process and what are the properties of an adiabatic process, and how they affect the work done in an isothermal process and adiabatic process. Okay, so I hope you all got the concept in the right way and revise it, and we will meet in the next class.